Hi, it's time for some notes and examples on decomposition reactions. This is following the lab portion of day 5 in the packet. We're skipping around a little bit, so day 5 is like day 3, I guess, for us. So decomposition reactions are reactions that start with one thing and break up into two or more products in a reaction. So we're going to look at some examples here together for our notes. Starting with, well, these are all based on thermal decomposition. Thermal decomposition is you use, energy from heat sources to try to tear apart compounds, decompose the compounds. We're limited to pretty low temperatures with Bunsen burners, although anything really, if you heat it up high enough, will thermally decompose. So, but for us, our first example is iron 2 oxide plus heat. Okay, so iron 2 oxide, let's get the formula of that figured out. I like to start a lot of my reactions with the formula equation instead of the word equation to try to figure out what's going on. So iron 3, that means it has a charge of 3 plus, and oxide, if you remember, has a charge 2 negative. So we're going to end up with a Fe2O3 for iron oxide. Now heat plus heat, I know it looks like it's not really a decomposition reaction because there's another component to it, right? Usually they have one thing in just the arrow for decomposition, but heat is facilitating the reaction. So it goes underneath the arrow as a triangle. Is how that shows up. Let's write all these out first, actually. So water is H2O plus heat, triangle under the arrow. And then we have hydrogen peroxide, H2O2 plus heat. Okay. Now we can talk about each one of these and what's going on. So iron oxide is way too strong for heat to actually break it apart. That's rust, by the way. So we have rusty vehicles. You can't just heat it up and it turns back to iron, right? You have to actually melt it down to its original form, and it ruins the entire vehicle. So this is not really obtainable here. That's an NR, no reaction. Okay, you have to molecularly blow that apart. And what happens when you heat up water? You make ramen, right? The water doesn't break apart and decompose, the water just boils. Okay, so this is also a no reaction. Or NR. Metal and non-metal oxides are actually really stubborn. They don't like to break apart. It has to be a special case in order for it to do that, and hydrogen peroxide is one of those cases, okay? As you should have seen in the lab portion of this, hydrogen peroxide does in fact break apart. We didn't test for this, but you can test to see that there is water in there. Hydrogen peroxide is really angry. It doesn't want that extra oxygen on it. So it will break off, forming water and oxygen gas. The oxygen gas bubbles up through, and you can test that with a splint to relight it to show that it does in fact have oxygen that's being generated. So this is creating water and oxygen. That's a typical decomposition reaction where it's creating two or more products from a single reactant, okay? So let's balance this. We do have a problem with our oxygens. The hydrogens are actually fine, but this is gonna give us an odd number of oxygens all the time. So I wanna put a 2 in front of my H2O, and that will give me 4 oxygens collectively on this side, which I can get 4 on the other side pretty easily. And it also does give me 4 of the hydrogens, which I do have 4 of the hydrogens over here on this side. So that worked out nicely for me on that side. All right, let's look at the next group of reactions. So these are metallic hydroxides. Metallic hydroxides are known to actually react almost spontaneously, but definitely when you have heat involved, they do like to decompose. So let's set up the beginning of all these just by looking at the words, the word equation. So we have barium hydroxide. Barium is a 2+, hydroxide is a 1-, so it would be BaOH in parentheses 2. This is, these are all thermal decomposition reactions, so we do have the plus heat with the triangle underneath the arrow there. All right, let's look at aluminum. Aluminum is, this is from the ion sheet, by the way. If you're, I just remember all of them, but aluminum is a 3+, hydroxide is a 1-. So that's a Al parentheses around the OH 3 this time, and the arrow with the triangle underneath it. And then the last one is copper 2 hydroxide. Copper 2 might not be a surprise, it is a 2+, just like our barium was. So we have Cu, parentheses around the OH, and a 2 there. All right, so what do these make? You might expect that they would just kind of blow apart and have aluminum and hydroxide flowing around. The reality is they can't do that. The reason they can't do that is because the metals are stubborn. They can't really go all the way to being by themselves. They actually get stuck in an oxide form. Remember, metal oxides, as we saw earlier over here, don't like to react. We had a lot of no reactions. It has to be a special case in order for that to happen. So what actually happens with the metal hydroxides is they lose some of it, but then they have to hold on to one of the oxygens. So we definitely have potential to make water, right? Because we have H and O in the parentheses, but we're going to end up with a metal oxide here as well. Let's look at the barium as our first example. Barium oxide and water is what's created out of that. And what you'll notice is that it actually balances itself here. We have barium oxide, BaO, and we have H2O being created as well. So out of one reactant, we have 2 distinct products, okay? Let's write those names up here. So we have barium oxide, plus, and then ran out of room there pretty quickly, water. Okay, so barium oxide and water for our products. That's what metal hydroxides do. They always make a metal oxide and water. So our aluminum is going to be aluminum oxide plus water. Our copper is going to be copper oxide and water. All right, so let's look at how those formulas look. So aluminum is different than the barium because it's a 3+. So in the in our formula, it's going to be Al2O3. Water is still the same thing, of course. Copper, though, copper does do exactly the same thing we saw with the barium, just because it has a 2+ charge. Okay. So we do have to balance this one. It's not perfect because of the way the charges worked out. So we do have 2 aluminum. That might be a good place to start. Try to get the aluminum back to balance. That distributes in here. So we actually end up with 2 aluminum and 6 hydroxides. That's 6 oxygens and 6 hydrogens. We have 3 oxygens here already. So if we wanted 6, we could multiply this by 3, and that would also balance our hydrogens. So that worked with a 2, 1, 3. This one balances itself, of course, down here because it's the same basic reaction that we saw in number 4. All right, let's name the, let's finish the word equation. So this is aluminum oxide. And water plus water. Not much room on these little boards here, sorry about that. And then this one we have copper 2 hydroxide, making copper oxide and water. So we have copper oxide. And water. Are the two products from that reaction. All right, so, and then the last group that we have to look at are the carbonates. I left the plus heat out of these. Hopefully it'll give me a little more room to write the products down. It might not, who knows, we'll find out. So carbonates are a lot like hydroxides in that they don't fully remove the oxygen from the metals. Again, metals are stubborn. They're going to end up with the oxygen kind of stuck on them, so they'll end up with metal oxides. But the other product is kind of novel and cool with these. So let's look at calcium carbonate first. Calcium is a 2+ charge, and the carbonates are a CO3 2 negative. So they go Ca, CO3. Let me write that up here. It's a CO3 2 negative, and calcium was a 2+. Okay. Now, I did leave the heat out of these, but they're all thermal decomposition. Let's just start them all as reactants, and then we'll figure out the products afterwards. So aluminum is a Al3+, carbonate again is a CO3 2 negative. So down here we have a Al2, parentheses are needed, CO3 3. And that's with thermal heat decomposition as well. Then we have copper 2. Copper 2 has a 2+ charge. Carbonate is also a 2 negative. So that's a Cu, CO3. These all do react. Carbonates react pretty easily, and they all make the same thing. They all make carbon dioxide. Okay, so this one's going to make carbon dioxide, CO2. This one's going to make carbon dioxide, CO2. And this one's going to make carbon dioxide, CO2. The only other part is the metal oxide that's left over. Okay, the metal oxide for this one would be calcium oxide. For number 8 would be aluminum oxide. And for number 9 would be copper oxide. Let's look at what the formulas of those are. So oxide is a 2 negative. Calcium is a 2+, so that's a CaO. Aluminum doesn't play as nice because aluminum, if you remember, is a 3+. So if it's with the oxide 2 negative, then we saw this just a minute ago, is a Al2O3. But copper down here does play nice and does about the same thing as our calcium did in the first one. It makes copper oxide as a CuO. Okay, so how does balancing work with these? Well, 7 and 9 balance each other without any issues. It's a balanced equation the way it's written. But we do have to do a little bit of work here with the, or do we? Yeah, we do. Because this has 3 carbons I can see right now. That's a problem. We only have 2 carbons over there. So let's try to get 3 carbons out of the carbonate. What does that do? So that gives us 3 carbons, and it gives us 3 times 2 is 6 oxygens. Oh, we had 9 over here. Oh, there's 3 over here. So yeah, that does add up to 9. So That's good. That did balance. So just the 3 there, so that's not too bad. All right, we need to name these. So in number 7, we have carbon dioxide. Well, in all these, we have carbon dioxide. And we also have, in this example, calcium oxide. Okay. And number 8, we have carbon dioxide. And we have aluminum oxide. And then in number 9, we have carbon dioxide right here. And we have copper oxide. So those are the reactions of decomposition. And again, it's very common that they have a metal oxide and some other product, or if they already are a metal oxide, they're not going to break apart for the most part. So thank you.